on centrifugation for large-scale clarification, 2000 liter continuous disk stack centrifugation remains the preferred method of operation. Centrifugation leverages the differences in density between solid impurities, cell debris, or flocculated impurities, and the product containing fluid stream. The benefit of centrifugation include the high volumetric throughput, the capability of handling high solid feed stream, and reduce process costs. Uh, the most common centrifuge design is a vertically mounted disc stack system. The cell culture feed is introduced at the axis of the bowl, accelerated to a target speed, often by radial vane assembly, and follows through a stack of closely spaced conical disc. Disk spacing is often between 0.5 and 3 millimeter to reduce the distance required for settling particles out of the fluid. The disk angle is often between 40 and 50 degrees to facilitate solid uh, transport down the disk surface into the solids holding a space for a solid bowl. The separating mechanism is as shown. The solid red dotted dots settle under the influence of centrifugal force against the underside of the disk and slide down the disk into the solid holding a space. Concurrently, the clarified fluid moves up the channel between the disk and leaves the centrifuge via a centripetal pump arrangement. The settled solids are discharged either continuously through nozzles or intermittently through ports at the bowl periphery. During centrifugation process development, a number of variables can influence clarification efficiency. The most common variables often evaluated include G-force, residence time, driven by the feed flow, the discharge frequency, cell density, and cell viability. The goal is to achieve a high level of clarification at the highest throughput possible and maintain process performance across scale. Cool for the summer. Disk spacing is often between 0.5 and 3 millimeter to reduce the distance required for settling particles out from the fluid. The disk angle is often between G-force provides the centrifugal driving force used to settle solid particulates against the conical disk stack at very high G-force. Excessive shear may cause cell damage and release of soluble impurities such as DNA and HCP. At very low G-force, solid may not effectively settle and may exit into the clarified centrate stream. Uh, residence time. The residence time is controlled by the feed flow rate Q. At lower flow rates, that is longer residence time, there is an increase in clarification efficiency as Stokes drag force is reduced. However, longer residence times reduce the volumetric throughput, which may be undesirable due to concern of product degradation and facility utilization. A balance between clarification efficiency and throughput is required for a robust and scalable primary clarification step. Discharge frequency. The discharge frequency for intermittent discharge centrifuge can also impact clarification efficiency as the centrifuge bowl or solids collection chamber fills. Solids begin to back up into the clarified stream. This can be observed by continuously monitoring the clarified stream turbidity, which will increase as the bowl reaches its holding capacity to reduce the breakthrough of solids due to overflowing of the solid bowls. A discharge and the frequency of discharge to reduce the loss of recoverable product protein in the supernatant fashion of the discharge stream. With each discharge, a portion of product in the supernatant is lost, which reduces yield. Solid settling in the bioreactor due to a lack of mixing that occurs near the end of the harvest operation. When the bioreactor volume is below the tank impeller, a safety factor of 70 to 80% of the bowl volume is commonly applied. The calculation of discharge interval is presented. At the point of solid discharge, it is common to observe a spike in turbidity due to destabilization of the centrifuge chamber. An additional concern with the solid discharge is the introduction of air-liquid interface, which may induce product aggregation or cause cell damage and release of process-related impurities. To mitigate the air-liquid interface, a pre- and post-discharge flush are often performed with a soluble process buffer or water. The cell density can have a significant effect on the clarification efficiency and yield for centrifugation processes. The discharge frequency is directly correlated with the cell density. As more cells are fed to the centrifuge, the rate of discharge will need to be increased. This can result in increased product loss due to more supernatant being directed to waste. At at industrial scale, the rate of discharge can also be limited by mechanical and automation limitations, which set a lower limit to the discharge interval. To overcome these limitations, the feed flow rate Q can be reduced or the feed stream can be diluted, which resulted in increased process time and process volume. Alternatively, a continuous nozzle centrifuge which discharges solid continuously can be adopted.